Hi everyone. So I need you guys to stop talking, please. Today we're going to continue on in Chapter 4. So in Chapter 4 we've been talking about inverse trig functions. In Section 1 we were primarily interested in how to compute like some of these inverses. And we did a bunch of practice concerning that. Here in Section 2, we're going to be looking at some applications. So Section 2 is going to be largely using the skills that we developed in Section 1 to solve other kinds of problems. So it's going to be largely kind of application-based, which is math code word for story problem. All right. Before we do that, though, I want to start with a little bit of vocab. So, rather than defining these things in words, I'm going to just kind of define them with kind of talk about what this is from a practical standpoint. The first thing I want to define is something called an angle of elevation. So imagine that you are this person, and you're looking up at the sun. So that's going to form an angle of elevation. So your normal line of sight, as if your head was not looking up or looking down, is one arm of your angle. And then the other arm is your sight line to whatever it is you're looking at. In this case, we're looking up at the sun, which is probably a bad idea in practice. He could be wearing sunglasses, but there's no sunglasses on the man in our picture, so he's playing with fire there. Yeah. I could, but I'm not much of an artist. I'm going to pass on that. You guys are allowed to sunglass your little man. My little man's going to need permanent glasses here in a moment. All right. The other option is, say he's looking down at his friend here. Again, from his line of sight to that downward angle, we call that an angle of depression. Not because his friend is sad, but rather because you're looking downward. Is everybody okay with that idea? Okay. So let's consider an example here. I should cut and paste these out of the notes. That makes more sense than to try to write this down. Too much writing, guys. So it says, Christy is looking up at the Fisher Building in downtown Detroit. She is standing 200 feet from the base of the building and finds the angle of elevation to the top of the spire to measure 66 degrees. How tall is the Fisher Building? First thing that I'd want to do in this situation is to draw a picture. Here's some ground. Here's my building. Okay. So we're told she is 200 feet from the base of the building. Would you like her, like, Pippi Longstocking haircut there? No, she's not looking at the sun, though. It could be sunny out. If you want Christy to have sunglasses, you can draw in some sunglasses. So it says the angle of elevation is 66 degrees. So there's that. Now, what are we going to be forced to assume here in this picture, or in this situation? Is I'm going to assume that Christy is, like, lying down on the ground. Why am I making that assumption? We don't know how tall she is, right? Because if she's standing, we don't know what that length would be, right? We're just going to assume that she's laying down on the ground and basically her height is 0. Joanna? Yep. All right. So if we resolve this picture now into a triangle, we have this. Everybody agree with that? What side am I looking for? The other leg, right? Everybody agree with that? So to solve for h, what trig function should I be using here? Tangent. So I can say tan of 66 is going to equal opposite over adjacent, or that h is equal to 200 times tan 66, which gives me 449.21 feet, approximately. If you get a nonsense answer, what is likely the problem? You're in the wrong mode. What mode should I be in to do this problem? Degree mode. Does everybody feel okay about what we did there? That's no big deal, right? All right. This example says, Jane has climbed a tree and is looking down on her friend Mary. Jane has climbed 17 feet into the air and the angle of depression to Mary is 49 degrees. How far is Mary standing from the base of the tree? What should I do first?
Picture.
Draw a picture. I'll try to draw a really nice picture, and that'll kill some time for you guys that are writing the words down. How's that? My Jane is definitely part bird. All right. So, we don't need to worry about that in this situation because Mary's not the one that's doing the viewing. She just has to stand there and look pretty with her purple hair and striped shirt. That's what she's looking for. Yeah, why not?
Is her head on the ground or is it
well, again, because Mary's not the one doing the looking, it doesn't matter if Mary's standing or not. And because Jane has climbed up into the air, we can just assume her line of sight. Okay, maybe she flew up there. Her line of sight is 17 feet. And which side are we looking for then of our triangle here? I want that side. I choose L for length. What did it ask for again? So this distance here would be the same as this distance here, right? Everybody agree with that?
I agree with that.
Okay. So what are we going to use to solve this? which says that L times tan 49 is equal to 17. Stop talking, please. And we divide both sides by tan 49. Gives us about 14.78 feet. Right. That's what she's going to swoop out of the air and attack. Did you like the bird feet that I drew on our person in the tree, though? Hi, Lexi. How are you? Oh, Sophie, for you. Yeah, you know what it's about. You're welcome. Everybody happy here? Okay. The answer is here, 14.78. That's okay. Maybe you're the one that needs the glasses. Oh, snap. All right. So this says Claude and Simone are riding bicycles in Paris. At one point, they look up and measure the angle of elevation to the top of the Eiffel Tower to be 32 degrees. When they pedal 100 meters closer to the tower, the angle of elevation changes to 37.5 degrees. How tall do they estimate the Eiffel Tower to be? So we'll start by drawing ourselves a picture. Are we still going to try to be winning art awards here? Oh, goodness. That's my Eiffel Tower. Well, that's why you guys all get your own sheets of paper. Definitely they are. This is the weirdest tandem bicycle also ever made because it has 3 wheels on it. Just so you know. It looks like a Dr. Seuss invention, actually. 3-wheeled bicycle or tandem bicycle. I don't have my graduate degree in Seussology yet. So this is our picture. Let's resolve this now into something a little bit less Yeah, chaotic, artistic, whatever. That's embarrassing. So we're looking for the height of the Eiffel Tower, and I'm going to call this other piece here X. So what I'm going to do with this triangle is I'm going to set up a system of equations to solve, because at first glance we don't really have enough information there. So using the 32-degree angle, I can say that tan of 32 is going to equal opposite over adjacent. What am I going to call the adjacent? X plus 100, right? Because the triangle that I'm using is this one. Everybody okay there? My other equation that I'm going to have is tan 37.5 is going to equal opposite over adjacent, because that is that triangle. Huh? Is everybody okay so far with what we've done? All right. So the first thing that I would do is I would rewrite these equations so that they don't contain any fractions. So if I clear the fraction on this, I would get this two equations. And now I'm going to make a substitution. Stop talking, please. Notice that both of these two equations are equal to h. So I can set them equal to one another. And now I'm just going to be using a little bit of algebra to solve this. So I'll start by distributing my tangent through. I'm going to put the x's on the same side and the non-x's on another. So I'm going to subtract x times tan 37.5 from both sides and then subtract 100 times tan 32 from both sides. On the left-hand side, both of these contain a factor of x, so I can factor that off. And now I can divide both sides by tan 32 minus tan 37.5. And at that point, it's calculator time. So nothing too fancy there once I wrote my system, right? Once I wrote my system, I just solved using substitution. And then I just had to get the x by itself to solve. But remember, what are we looking for in this problem? We want the height of the Eiffel Tower, was what we were asked for. Is x the quantity we're really looking for here? No. What are we really looking for? H. How would I find h? I can just plug this back in, right? So, for example, I could do 438.64 times tan of 37.5. And that's going to give me 336.6 meters. And that's actually what I'm looking for. Everybody okay with this idea? All right. What is our schedule today? Everything is basically the same. This is way too early of a place to end at. I know, I'm excited too. We get to do some more. I can't spell today, folks. All right, so let's move on then and start talking about section 3. Don't act like we've never done this before. I understand that you didn't like it last time we've done it, but we've done this plenty of times before. This is what happens when there's no homework quiz, though, right? We can cover more stuff in class. All right, so we're going to start here today. And really the only application that we're going to be interested in is course or bearing. So, we use like a bearing frequently when describing directions, especially in things like airplanes or ships where there's not necessarily like roads to travel. Or if you're like, you know, like an Army Ranger unit and you're like hoofing it through places where there's no real roads per se, often are going to be communicating in bearings, because you're not going to just be like necessarily driving down roads to get someplace. You have to like be sneaky. So, a couple of things to keep in mind from bearing. Angle measures are going to begin at north. And we're going to measure angles clockwise. How does this jive with what we've been doing when drawing our angles in standard position? Is it the same? Definitely not. And that's the unfortunate part. So if we're talking about a bearing of 72 degrees, I'll start by drawing my compass rose, which looks an awful lot like the XY axis. And I'm going to label it northeast, southwest. Yeah, whatever you want to say. And if I then go 72 degrees clockwise, the angle that I'm going to be interested in is here. Everybody agree with that? In our standard way of measuring things, we would go here, and this would be an 18-degree angle. So a 72-degree bearing was equivalent to an 18-degree angle. Okay, so we have to be a little bit careful in making sure we're drawing a picture nicely and then are able to translate our bearing into an angle. So I want to make sure that we're comfortable doing that. Additionally, I guess I should add in one more bullet point. Bearings are measured from 0 to 360 degrees. Notice there the bracket and the parenthesis. So 0 is a bearing, 360 is not a bearing, but we can go right up into 360. Yes, of course. So let's do a little bit of practice here. So I'm going to write down a couple of bearings. SP is just standard position. And I realize that this may seem a little trivial, but if you can't do this part, like, it's going to be real difficult to get correct answers. So again, what we're asking you to do here is we're going to take these 4 bearings and convert them into angle measures measured in standard position, kind of in the normal way we've been measuring angles. Hopefully this is going to be big enough for what we want to do. So 58 degrees, we're starting at north, and we're going, say, 58 degrees to get here. What would this be? Oops. Going with a normal angle. How much would this be? 32. So if I do 164, everybody agree with that? Okay, so the angle that we're interested in then would be this one. How much is that? $164? What do you mean, how is that 164? Yeah, that's the beta symbol. 286 is correct. So what David did was he figured out from here to here is 16, because 180 minus 164 is 16. And then he added 90, 90, 90, and then 16 more is 286. Everybody okay with that? All right. Next one is 221. So 90, 180, and then some more. So this angle is, we're looking for is that one. Everybody okay there? How big is that one going to be? $229 is correct. So the way we did that was we knew it was 90, 90, and then 41 more to get to here. So that means that this portion has to be 49, excuse me. And then 90 plus 90 plus 49 gives us the 229. And the last one is 299. So 90, 180, 270, and then 29 more. So the angle we're looking for then is this one. What did you say it was, David? 160? That doesn't seem right. Yeah, that seems better. So the way we did this was we noted that this much was 29, which means that this side is going to be 61, and then 90 plus 61 gives me the 151. Yeah. We just did 4 examples. You're just like adding or subtracting from 90? So like the 229, so to do the 229, we went, 90, 180, 270, so this section here is 29. 90 minus 29 is 61, right? So that's that other side. So to go from 90 and then 61 more is the 151. That's all we're doing. A boat leaves a port and averages 40 knots, traveling for 2 hours on a course of 215 degrees. Then the boat turns to a bearing of 162 degrees and travels at 55 knots for 3 hours. What is the distance and bearing of the boat relative to its starting position at the port? How many of us are in a physics class right now or have been in a physics class previously? A handful of us? If you are, what we're about to do should look relatively familiar. The idea for a problem like this is we're going to break down these into components. So this first piece of information, we're going to break this down into like a vertical and horizontal component. And then we're going to break our second part down into a vertical and horizontal component. After that, we can add the vertical components and the horizontal components of the two different parts of our trip, and then use the Pythagorean theorem to find out the total displacement, or the total distance we are from the start, and the angle that we are relative from the start. So to do this, I'm going to just draw a series of pictures. To assist me in doing this. So for the yellow part of our trip, I'm going to be looking at this picture. So 40 knots for 2 hours. How many knots are we going here? 80 knots. Everybody else okay with that? So if we go for a course of 215 degrees, we start at north, and we'll go 90, 180, and then like 35 more. But remember, we're not interested so much in the bearing as we are in the angle measure from standard position, which would be this. So to calculate this, we're going to do 90 plus 90 plus 55, because 90 minus 35 is 55. So I get that my angle alpha is going to be 235 degrees. I'm going to call this alpha. So, just in a little bit of a cleaner position, we have this guy here. I want to know its horizontal and vertical movement. So to do that, I can just do 80 times cosine of 235, and then 80 times sine 235. Because this side length is 80, right? What's the advantage of me using 235 here rather than whatever this angle would be? It'll give me the sines automatically. I don't have to worry about remembering to write my sines in. So that's the advantage of using 235 there instead of 55. Because then I'd have to go back and remember to put my negative signs in. You could do it that way, but that's one less thing for me to forget to do. Is everybody okay with how I did that? So this is what I'm going to hold on to. I'm now going to do the second part of my trip, the part in green. If I go 55 knots for 3 hours, how many knots have I done? I think 165. and then I'm going to do the same kind of thing. So I'm going to start with my bearing, which was 162 degrees. So 90, and then 72 more is going to put me over here. But remember, I want this as a standard angle. So this is going to be 90 plus 90 plus 90 plus 18 more. So I'm going to call this angle beta is equal to 286. I mean 288. Goodness gracious. So, again, what we're trying to do now is I want to take this angle and resolve it into like, horizontal and vertical components. To do that, I'm just going to take the magnitude times cosine of the horizontal component and the magnitude times the sine of the vertical component. So when I do that, I get the point 5.10, comma, negative 222.46. So I just added the x1 and x2 and the y1 and y2. And what that tells us then is that our final position after the trip is something like there. So I need to do two things to finish this off. I need to know how long is that arrow, and I need to know what is this bearing. So we figured out where the boat is going to be at the end of this trip. We just now need to be able to communicate that in a distance and bearing. So let's answer the how long question first. how long is that arrow? How can I calculate how long that arrow is going to be? If I want to know how far is it from this point to this point, what would I use? Joanna? Sure. Yeah, I could use basically the distance formula here, but since the origin is one of the points, this resolves down into the Pythagorean theorem. Which comes out to be 222.51. And really, I guess, knots is a ratio, like it's nautical miles per hour. When we said 80 knots before, it really meant 80 nautical miles. So the answer here is in nautical miles. Everybody okay there? Everybody okay with that? Now, to figure out what this bearing is, I'm going to first calculate maybe I should use another color here. Stop talking, please. We're first going to calculate what is this standard position angle, and then we're going to convert that into a bearing since we don't have a tool to go directly from an angle measure or from this point to a bearing. So I know that I can do this using tangent. Because I have a y and an x. I remember from our unit circle definition of tangent, tangent is y over x. When I type this into my calculator, though, I get negative 88.69 degrees. What that's going to tell me here is that this angle is 88.69 degrees. So my bearing is going to be 90 plus 88.69. which is 178.69 degrees. So let's do one last thing on this to just see if this answer that we have makes sense. Okay? So, my trip, it says, I start by leaving at a bearing of 215 degrees. So 90, 180, and a little bit more. And we went 80 total knots. So I'm going to draw another kind of units, or another kind of cart, or compass rose. And now from this position, I'm going to find 162 degrees, which is 90, and then like 72 more. And this time I'm going 150 whatever knots. 155 is what we said. And really, I mean nautical miles here. So that should be like twice as long as the other one was. Everybody okay there? So if I look at where I'm at, is that about the same position as what we described at 5.1 negative 222? Looks about the right spot. Everybody agree with that? So I feel pretty confident there that I've done that correctly. So we'll stop here. Check later this afternoon. I will post an assignment.